Okay, good afternoon, everyone. So, in the previous yesterday, we spoke about the operators and their eigenvalues and eigenfunctions, eigenstates. I've told you that in quantum mechanics, every observable, every measurable feature of the system, in quantum mechanics, you can correspond to this observable some operator, which for which you can solve the you can solve the eigenvalue problem. It that kind of problem. So that means that if you act by this operator on the eigenstate, this eigenstate shouldn't change except for multiplication by some number. And we've solved a couple of problems to demonstrate how does it work. Especially we find out we have found eigenfunctions, eigenstates for a system having the given momentum, and we found that the plane waves are these eigenstates, eigenstate of the system or particle that have given momentum p. And we found eigenfunctions in eigenvalues of the angular momentum operator. And we found that the angular momentum quantizes, meaning that angular momentum has a discrete spectrum. It can have only discrete number, not discrete number, only discrete values that can be found in the experiment. And we have found these values as well as just a number times some number times h. The last thing I want to say in this, I gave you a homework. I think you will solve it without any problem. The last thing I want to say you that lately we have spoken. I have told you that I have told you that the state in quantum mechanics can be either some function or a vector, a, b, or a vector of functions, but it's not, we wouldn't speak about that now. So, for functions, if the state is represented by functions, the operators, we discussed what is operator. Usually it is a differential operator or some kind of multiplication operators. So you either you either differentiate your take derivative of your states with respect to several variables, or you or you multiply the function on some function of coordinates. Another option is when your state is given by some vector. Sorry, somebody asked something, or it was just...
No.念，这только что我是同学们关一下自己的麦啊，再认真看一下。
Okay, thank you. What are operator in the case of when we set the state as a vector? Obviously, we've spoken that operator just transfers one state to another state. It's the definition of the operator. Some operator. So in function, if we work with function, the operator can be derivative or multiplication on some function. In the case of vector, what object transfers one vector to another vector, C, D? Probably you know this object. This object is a matrix. So in vector representation, we call it representation when you represent the state either by a function or vector. In vector representation, the operator is a matrix. So you have some, let's say, some matrix A, B, C, D, acting on, let's name it F1, F2. And if you act by this matrix, and acting by the matrix on the vector is just a multiplication of the matrix and the vector, and then we have AF1 plus BF2 here, CF1 plus DF2. So it is just a matrix operation. Here you should remember what I have said in the first lecture when I've told there were two ways to formulate quantum mechanics. Was the wave mechanics proposed by Schrödinger, and was matrix mechanics proposed by Heisenberg. And this kind of stuff, this approach is works in Heisenberg matrix mechanics. So, and the problem of eigenvalues and eigenvectors formulate pretty simple in the matrix form. You probably have the course of analytical vector analysis, analytical geometry, where you know that if you have some matrix, you can find the eigenvectors and eigenvalues of this matrix, solving the equation A times B equals to some eigenvalue lambda times B. And is we can, as an example, we can take the most simple, not most, but very simple matrix. Let's take A equal to 1, 0, 1, minus 1, and find out what is the eigenvalues and eigenvectors of this matrix. Okay, let's do it. Let's calculate. Let's write down this equation explicitly. We'll get 1, 0, 0, minus 1. The vector b would be given by b1, b2 equals to lambda b1, b2. First of all, from the analytical, from the linear algebra, or I'm not sure how they call it in your university. We call it linear algebra, I think. You know the eigenvalues of some matrix can be found in the following way. You write down the matrix and substitute the lambda from the diagonal elements, minus lambda, 0, 0, and take the determinant of this matrix. So I substitute lambda only from the diagonal elements, and keeping the off-diagonal elements same as they were. Here they are zeros, that's why zeros, and find the determinant of this matrix. The determinant of this matrix equals, as we all know, to 1 minus lambda, minus 1 minus lambda, equals to 1 minus no, equals to lambda minus lambda squared minus 1. And we equate this determinant to 0, and the solution of this equation gives us the eigenvalues of this matrix. We see that eigenvalues are lambda 1 equals to 1 and lambda 2 equals to minus 1. And then we can find the eigenvectors, substituting substituting lambda by its value. So let's put it here, the lambda 1. So let's calculate it. B1 minus B2 equals to B1, B2. So we have a set of two equations. B1 equals to B1, B1 equals to B1, and B2, and B2 equals to minus B2. The second equation gives us 2B2 equals to 0. That means that B2 equals to 0, and this equation is trivial, and we cannot find B1 from this equation. However, we already know that the first eigenvector, therefore, the first eigenvector is given by the vector B1 not B1 0. How do we find B1? First of all, you see that this the equation, the eigenvalue problem, it gives us the vector up to some multiplier. I can multiply this vector by any number, and the equation will still be held. That is why this B1 couldn't be found from the any vector with any such vector would be the solution of the eigenvalue problem. That is why we need to put additional constraints on this vector. And in quantum mechanics, you know that such constraint is the normalization constant, mean that the square of this vector should equal to 1. So square of this vector is b1 squared plus 0 squared equal to 1. That means that we can set b1 equal to 1. And that means that the first give me a second. Oops. Sorry. I'll put it later. Okay. So the first eigenvector is just 1 naught. The first eigenvector, 1 naught. Let's say v1 equal 1 naught, lambda 1 equal to 1. So what about the second eigenvector? We can write down quite the same thing. 1, 0. Let's write down this equation by putting lambda equal to minus 1, because the second v2 equals to some vector and lambda 2 equals to minus 1. So our matrix and the vector b1, b2 equals to minus 1, b1, b2, b2. So let's multiplicate, we get b1 minus b2 equals to minus b1 minus b2. And here we have vice versa. b1 should be equal to minus b1, therefore b1 should be 0, and minus b2 should be equal to minus b2, so we do not know what is b2. And consequently, our vector, our v2 equals to 0 b2. And b2 can be found from the normalization conditions, and we already know that b2, we can set b2 equal to 1, and that is why b2 equal to 0, 1. 0, 1. So this vector, this matrix has we have found two eigenvectors, 1, 0 and 0, 1, and two eigenvalues, plus 1 and minus 1. And what does it mean? It means that physical quantity that stands before this matrix has can have two values, plus 1 and minus 1. And the eigenstate corresponding to plus 1 can be written as the vector 1, 0, and the eigenstate standing for minus 1 can be written as 0, 1. Well, you can ask me, what is this physical quantity that comes in that way? And I will say that I'm just going a bit forward, and this quantity is a spin, is a magnetic moment of the particle, or we can say electron, and this magnetic moment can have two values, either plus, usually it is plus h halved and minus h halved, but it doesn't matter because all this the multiplicator it depends on the matrix. I can multiplicate matrix by h halved, and then I will find that my eigenvalue will become not minus 1 but minus 1 times h halved. So this matrix, it's the matrix standing for projection of the spin on the z-axis. We'll prove it later. I just bit going forward, and we have found that this observable, the projection of the spin on the z-axis, can have two values, plus 1 minus 1, or plus h halved minus h halved, and it has the eigenvectors corresponding to these eigenvalues is 1, 0 and 0, 1. 1, 0 means that the particle has magnetic moment plus 1, minus 1, plus 0 means that with probability 1, that means that with probability 1 I will measure the value plus 1, and with probability 0 I will measure the value minus 1, and that vector means that with probability 0 I can measure value plus 1, and with unit probability, with probability 1, I will measure the value minus 1. So that is another way of representing the quantum mechanics, the matrix way, and we will use that approach later too. So I was speaking about I was speaking about operators. However, not every operator can be, not every operator can represent the physical quantity. Uh, we uh, the the nature it mm, the nature sets some limitation on the some restrictions on the operator, and the main restriction is that the average value of physical quantity should be real. So what you are measuring in the quantity that you're measuring in the experiment should be a real number. You cannot measure complex numbers. And that means that that means that uh, oops, sorry. Uh, so the average value of the observable f should be a real number. But how do we formally, mathematically um, define the real number? We define it in the following way. We say that this number, the complex conjugation of this number, should be equal to itself, because we know that complex conjugation of, let's say, 2 equals to 2, but the complex conjugation of 2 plus 1, 1 times I equals to 2 minus 1 times I. So these two values, these two numbers are not equal. That is why they are not real. So f average f should complex conjunct should be equal to itself. But we remember that the average value. We remember that the average we can write down the average value with help of this equation. Okay, we can conjugate this integral. Conjugation of psi conjunct will give us psi, and the conjugation of f psi would give us f conjunct and psi conjunct. Note that conjunct operator is defined in the following way. If we have some operator acting on psi and giving some function phi, then conjunct operator acting on the psi conjunct should give us phi conjunct. So that is the definition, not the definition, that is the condition of reality of the reality of average value. So not every operator can be not every operator satisfy this condition, but what operator do satisfy? Before answering, we must introduce, we have introduced already the concept of conjugated operator, F conjunct. Then, after that, we have to introduce the concept of transposed operator. What do you mean? You know what is transposed matrix is. The transposed matrix is a pretty simple thing. A, B, C, D transposed equals to AC, B, D, B, B, D. We just rotate the matrix in 90 degrees. Okay, not rotate, but we we transfer the rows into the columns. So the row AB becomes column AB, and row CD becomes the column CD. So that's our transposition. But what is transposition in the operator terms? The transposition in operator terms is given by the following equation. You see, if you multiply, if you have this integral, different functions, f times f phi times f acting some function psi, the transposed operator, this integral equals to the same integral with transposed operator, but the act of the integral transfers to the first function. So we just transfer this operator to this function, and then we can call it transposed. At the same way, we can define the transposed matrix, because if we take matrix if1 f2 vector no if we take the following product, f1 f2, here a b c d, and here g1 g2, then the transposed matrix would give us okay, we can make it in that way: g1 g2 a b c d f1 f2. So that's and this matrix is transposition of this matrix. You can see it because let's multiply if we multiply this matrix by this vector, this vector by this matrix, we find out we should multiply as a first row we get a g1 plus b times g2, and here you see the same thing. If we multiply this vector by this matrix, from the right, we get g1 times a plus g2 times b. That's the same thing. So that is the definition of the transposed operator, and the definition of the transposed we know the definition of the transposed matrix. So let's compare this equation with this equation. I'll put it here. You see, if you want to ask me, please feel free to ask. You see that if we look in this on this equation, the psi, we can, if we set the phi equal psi conjunct and psi equals to psi, we will get from here we will get integral psi conjunct f psi equals to psi f transposed psi conjunct. And if we look on this integral, the condition of reality of average value, we see here we have this integral, and here we have this integral, except that for to satisfy this condition, we have to demand from the operator to be equal, the transposed operator should be equal to its conjunct value. So, and that is the limitations. That is the limitations that is set on our that is set on the operators of physical quantities. They're transposed. The transposed operator should be equal to the conjunct operator. And here I should remember you about that in if you work in matrix terms, the operator is the matrix, and in matrix term, this equation would read as this condition reads as transposed matrix should be equal to equal to conjunct matrix. So if you're working with functions, you define the transposed operator as this, and if you work with metrics, the condition of that for that matrix to be the matrix of physical value, or that the average physical quantity to be real, is that the transposed operator equals to conjunct operator, or in the same way the transposed matrix equals to conjunct matrix. We will these operators or matrices that satisfy these conditions are called Hermitian. That's Hermitian operators or matrices, as you want. So let's look on the matrices. We will test some operators later, but we can easily test metrics. So let's define some metrics. 1, 1, I, 0. So, do you think this matrix is Hermitian or not? So I give you just a minute. Not, you're right. Yeah, because the transposed matrix is given by 1, I, 1, 0. Yeah, and then that is transposed, and that is conjunct matrix 1 minus I, 0, 1, and we see that matrices are not Hermitian. Another example is the matrix 0, 0, I minus I. So what do you think about this matrix?
Hermitian.
Yeah, it's that's a Hermitian matrix because transposed matrix. The transposed matrix is 0 minus I, 0, and conjunct matrix is, we should just change the sign, 0 minus I, 0. So they are equal. The last thing I will write here, at the same, you can the conjunction of the conjugated matrix or operator gives us the same the operator. That is why we this condition can be written in the following form: f transposed and conjugated should give us F, or A transposed and conjugated should give us A. And in this case, we can transpose it. Okay, minus I0, then conjugate it. Conjugation changes the sign, so plus, and we see we came to the same matrix. And here it will give us 1, 0, I1, and we will change the sign. So this transposition do not equal. So the operators of physical quantities should be Hermitian. And if your operator is not Hermitian, that means that you cannot use it for description of some physical quantity, but it doesn't mean that you cannot use it in quantum mechanics. We will see later that we use some non-Hermitian operator in quantum mechanics mathematics, but they do not represent some physical quantities. There are very nice properties of Hermitian operators and matrices. The first one is that the eigenstates, eigenfunctions of this operator are orthogonal, meaning that this integral give us the Kronecker delta symbol, delta mn. You remember that delta mn means that equals to 1 when m equals to, when m equals to n, and 0 when m do not equal to m. So finally, I just recall that the Hermitian operator, the operator can be called Hermitian if you, for any functions psi1 and psi2, this integral equals to this integral. Actually, in quantum mechanics, we'll see it. We put some conditions on these functions. So not any function, but the function that decays into infinity. We're working on only with operators acting on the acting on some localized function that can that equals to the 0 at the infinity. At least we do that when we prove or disprove that some operator is Hermitian or not. The Hermitian conjugation is the linear operation. That means that if we take the Hermitian conjugation of some of the operators AB, it will give us the sum of Hermitianly conjugated operators. As for conjugation of product of the operators, the conjugation of the product is the product of the conjugated operators, but standing in the reverse direction. So AB conjugated equals to B conjugated times A conjugated. Actually, that stands for ordinary matrices, because we know if we want to transpose A, B, we will get B transpose times A transpose. And the last thing, that the conjugation of the conjugated operator gives us, so it's a reversible operation. The double application of this operation, the conjugation, should give us the same operator. So let's we'll solve this problem later. Let's solve this problem. We have this the momentum operator, and let's check that this operator is Hermitian. Okay, let's copy this this condition and substitute F by P. Okay, what we have here, psi1 minus IH times d psi2 derivative dx d dx equals to should equal to integral psi2 times, so what is the complex conjugation of this operator? Is just conjugation of this imaginary unit, so it should be plus I h d dx, because we remember that the px conjugated on some function f conjugated should give us g conjugated if px f gives us g. So conjugated operator here plus plus IH times integral psi2 df1 conjugated derivative dx. So we have to check whether this integral equals, I'll put it to there, whether this integral equals to this integral. So it looks like that they are not equal, but however, let's take this integral by parts. What we will get? We will, I don't know how it is in Western. Okay, let's put it in that way. We say that d psi 1 0 dx is sum dv, and psi2 is u, and then we should IH is, and then this integral gives us u times v, v, then v equals to just psi1 conjunct, and so we should write down v times u. So, it means that psi conjunct times psi2, and the integral is performed over the whole x-axis, minus infinity plus infinity. Here minus integral du equals to d psi 2 over dx and dx. Okay, psi 1 conjunct d psi 2 or dx over dx minus infinity plus infinity. So you see that this integral equals to this integral, because we have minus here, this minus, and this I times h. And we're still having this term. But as I said, when we proved the Hermitianness of this operator, we assume that it applies on the localized functions, meaning that the functions decay in the infinity. And that means that psi1 and psi2 should be equal at the infinity. And that means that this term equals to 0. So that brings us to the following equation, minus h. The right hand side gives us minus infinity plus infinity psi1 conjunct d psi2 divided by dx equals to the very same thing, minus h integral. Okay, that's the very same integral, psi2 dx. That means that operator px satisfies the condition for Hermitian operators, and that means that operator px, operator of the projection of the momentum on the x-axis, is Hermitian. That is not surprising, because we know, we have postulated, we know that px is the operator that stands for momentum, that is the physical quantity. Okay, yeah, that's the solution. Let's take another operator, the operator of conjugation. And let's find out whether the operator of conjugation is Hermitian or not. Here's the definition of the conjugation operator. So, what do you think? What we have to begin with is to define the conjugated operator C. We know that conjugated, as a definition, C conjugated acting on psi conjugated should equal to psi, because psi conjugated equals to psi. And you see that conjugated operator C equals to itself. C conjugated equals to C. Here's the condition of the Hermitian operator. Okay, we already know that C conjugated equals to C. That means that this integral equals to psi2 times psi1, and this integral equals to psi1 conjugated times psi2 conjugated. We see that this integral do not equal to this integral if we're working with complex functions. However, so the operator of complex conjugation is not Hermitian unless we are working on the domain of the real numbered functions, and in that case he would be Hermitian, but we do not work in. We work with complex numbers, so C is a Hermitian operator, non-Hermitian operator, is not Hermitian operator. So let's solve let's solve this problem, p squared x, whether it is Hermitian or not. I'll give you just 5 minutes. 5 minutes. Yeah. And we will solve it. Note one thing: if some operator f, if it Hermitian, then multiplication of the operator by some real number, a f is still a Hermitian operator, because multiplication af is Hermitian operator. But if we multiply by some complex or imaginary number, ai f is not Hermitian, because while Hermitian under under procedure of Hermitian conjugation, you take the complex conjugation, and even if and that means that okay, let's do it that way. The Hermitian conjugation of the imaginary unit is just imaginary unit is a number, and so the Hermitian conjugation, you cannot transport the transposition of the some number gives the same number. That means the conjugation of the some number gives us just a complex conjugation. That means, so the complex number are not complex number are not Hermitially conjugated. That means that in that case, if we conjugate AIF, we should take F conjugated, A conjugated, I conjugated, I conjugated, and A conjugated. A is a real number, so conjugation of A equals to A. I is imaginary unit, conjugation of I equals to minus I. It would give us F conjugated times A and times I. And here we see that it do not the conjugated, this conjugated operator do not equal to F conjugated. Yeah, and if F conjugated equals to F, we have a I F with single sign minus. So conjugation of this operator, if F is Hermitian, will give us minus AI F. So this is so-called anti-Hermitian operator, meaning that if you Hermitially conjugate it, it will change the sign. So, sorry. Try to solve this. Try to prove that this operator is conjugated, Hermitially conjugated. Not is Hermitian. Actually, you can do it two ways. By direct applying the Hermitian condition, as we have done for operator P, and a bit more tricky way. Let's see, can you find it? First of all, I'll do it easy way. First of all, you see that 2m is the real number, so we do not need to bother with this multiplier. We just need to check whether the p x squared is Hermitian. I've told you that we have found that multiplication of the Hermitian operator Hermitian conjugation of the product of operator is the product of the Hermitian conjugated operator reversed. So px squared conjugated equals to px times px conjugated equals to px conjugated, which is px conjugated, px conjugated squared, because it's the same operators, and that's the same operators. But we know that px is a Hermitian operator, meaning that px conjugated equals to px. That means that equals to px squared. That's simple. The another way to do that is to remember that px px squared equals to, remember that px equals to minus ih dx, px squared equals to minus h squared, the second derivative over the x. Again, we can omit this real numbered multiplier, and can check the only Hermitianness of the second derivative. We can do it, so we should check this integral. We should check this integral, c1 conjugated, the second derivative of psi2 dx equals to, okay, dx equals to psi2. So the it is a real numbered operator. That is why there are no need to complexly conjugate it. That means that we just write dc1 conjugated dx squared x. That's integral. Then we can do the same trick. We can integrate it by parts twice. I will do it in a fast way. So this integral, it give us, I'm sorry, I will do it in a fast way. That means that psi2 times psi1 my dx minus d psi2 dx times d psi1 dx equals to, this one gives us 0. As we remember, we consider the function decaying in the infinity. That means that we need to look only in this integral. So we are integrating by parts one more time. It would give us the psi2 dx times psi1 plus, should be minus infinity plus infinity. And here we have psi2, the second derivative of psi2 dx times psi1 dx. We see that this equals to 0 too, because function, we assume that the function decay in infinity, and we got the same, or I have forgotten about the complex conjugation near psi1. So we have the same integral, and that means that this operator is Hermitian. So let's take a 10-minute break. Thank you. And we will move to the commutators and measurement problem. So we have spoken about the operators, and we spoke about I'm sorry, uh, about multiplication of operators. Now I want to go deeper into this multiplication, but before, uh, so what is multiplication of operators? Let's do that way. It is when one function, operator, let's say f, acts on the result of the acting operator g on some function, let's say phi. And that is critically linked to the measurement procedure. And let's talk about, we already talked about coordinate and momentum that cannot be measured simultaneously. But what do we mean by measuring simultaneously? I think that's a critical point in quantum mechanics. There are two ways of learning quantum, not two ways, but two sides of quantum mechanics. The mathematical side, obviously you should understand and know all the problem, how to solve problems, how to solve practical problems. And another thing is understanding what is under these equations. And it is, I think it's very important part, because somebody can operate with equations without fully understanding, but understanding of quantum mechanics is still a very important thing. So what does we mean by saying that we can simultaneously measure both let's say value observable f and g? It doesn't mean that we can measure it, we possibly can or cannot measure it in one moment of time. It means that I can measure the value g and find out that the system has value of this observable gn. Then I can measure the observable f and find out that it has. I think I should draw it in that way. That's the system. It goes through the instrument f, and we find out that we have f, let's say f1. Then we put the we f2, f3. We didn't get f2 and 3, we got f1. So let's say it is an electron going through the instrument, and it as in Stern and Gerlach experiment, it just this electron just changed its trajectory to the upward way, not down, not straight, but upward way. Then we put this electron through some another instrument G, and we get some, let's say G2. We do not get G1, we do not get G3, we do not get G4, but we get G2. So can we say now that we know about this system, about this system that came from this, or the second instrument, that we know that this system has uniquely unambiguously defined values of f and g observables, that and f equals to f1 and g equals to g2. So In classical mechanics, yes, we can say, because we measure it. At the first time we have measured F1, and the second time, and the second moment we have measured uh, observable G, and find out that this observable is equals to G1. We can measure the particle uh, at the first uh, as the first experiment. We can measure the coordinate of the particle, just switching on the light and just taking a photo, and then we can measure the momentum, taking a video. We can take a video and just calculating the velocity of the particle. But in quantum mechanics, it is not so, because if we put this particle, if we put this system through the instrument F again, we get F1, we can get F2, and we get F3. In general speaking, we would not get F1 with probability p equal 1. No, we get F1 with some probability less than 1, and we get F2 with some probability greater than 0. And that means that these two values cannot be measured simultaneously, because if these two values f and g could be measured simultaneously, it means that after the repeated measurement, let's say we measured, we have found f1, g2, then if we measure value f, after, if this, let's say, if values are simultaneously if we can simultaneously measure, then we get f1 with some probability. We get f1 with, actually the probability of getting is some, we don't know, but some p1 that is less than or equal to 1 or and greater to 0. Then we get g2 with some probability, let it say p2, 1, and then if these values can be measured simultaneously, we measure f, we measure g. If we measure f one more time, we'll get f1 with probability p equals to 1. And if then we measure g, we will get g2 with probability p equal 1. That means that we know both values of f and 1, because no matter how much time we would measure this value, these values, and no matter in which order we would measure them, they would be we would get every time f1 and g1. But if they are not measurable, simultaneously, then measuring f with some probability p1, 1, we get f1, then we get g2, and then measuring f, we get some fn with probability pn less than 0 and less than 1 and greater than 0. So after the second measuring, after the second measurement of observable f, I can get almost any value from the discrete spectrum of f. I would not get f1 with probability p1. I can get f1, but the probability of that would be less than 1. And that means that these values cannot be measured simultaneously. That means that the moment I have measured the value g2, the information about the value of f that is equal to f1 has been erased. This information has been erased, and we know only g2 value. And as the next step, if I measure g here, I wouldn't get g1, g2. I would get some gn with some probability, with some unknown probability, not unknown, we can calculate. That means, and that is a very important thing, that what we mean saying that the values can or cannot be measured simultaneously. If you can measure, no matter how much time and what is order of measurement, if you with if you with unit probability would get f1 and g2, then you can measure these values simultaneously. But if after the measurement of g1 value or of g value, the information about f is erased, then you cannot measure both values simultaneously. Going back to the example of trajectory and momentum, let's look what we mean. We mean the following. We can measure the momentum of the particle somehow. Let's we know that the momentum of the particle. Then we measure the coordinate of the particle. We try to measure it. But how do we measure it? The only way to do that is interacting with this particle by means of another particle. The easiest way to do that is to use photon, where we collide the photon with this particle with known momentum, and we get information about the coordinate of the particle. But collision of the photon with the particle changes the momentum of the particle, and that means that in the next measurement of the momentum, we will get another momentum, not the one we get at the beginning. So that's what we mean by simultaneous measurement. And what do we mean? Let's put it in mathematical terms. Let's we have some state psi, and we want to measure observable f. We know that after measurement, if we want to measure f mathematically, we have to decompose psi into the psi, no, let's say phi n, where phi n is the eigenstates, eigenfunctions of f. Say f phi n, it gives us fn times phi n. So we decompose our state into the, we can decompose our states into the eigenstates of the operator of this observable, and these coefficients an gives us the probability of getting Fn. We get with probability Pn equals to an squared. Okay, then we want to measure the value g. To do that, what we need to do mathematically, we need to decompose the function fn because after the measurement, that is another very important point. After the measurement, I'm sorry, fn, it's fn, and after the measurement, the state of our particle, it was psi, but it after the measurement it becomes f phi n. So after the measurement, during the measurement, the nature or the instrument randomly chooses one of these phi n and puts the particle at the state phi n with probability that is equal to the square of this with probability that equals to the square of the coefficient of the decomposition. So after the measurement, the state of the particle changes. It was psi and became phi n, and it became it happens randomly. We get instruments show us value fn, and we know that the particle state is phi n. Okay, we know it. Then we want to measure the value of the observable g. To do that, we should decompose fn into the series, let's say m, of the eigenfunctions of operator g. What function? Let's say it would be hn equals to gn times hn, where hn is some functions. It's eigenfunctions of g. Okay, coefficients bn times hn. So we have to decompose our particle, our new state psi n, into the eigenstates of the observable g. Okay, and with the probability bm, we will get gm with probability gpm equals to bm squared, and we get the state hm. See, after the first measurement, our system was in the state phi m, and after the second measurement, our system becomes at the state hn. And so, if we want to measure our value f one more time, what should we do? We should decompose hm into the eigenfunctions of the operator f. So sum a, it's not a, but it's new coefficients c, cn phi n, and with probability pn equals to cn squared, we will get fn psi n. and this n, okay, let's say n1, 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 n1. So at each procedure of of measurements, mathematically, we decompose the input states into the series of the eigenstates or eigenfunctions of the operator of the value we measure. Then instrument randomly choose the state with probability that is given by the coefficients of the decomposition. And we can ask ourselves, and what is happening if our values can be measured simultaneously? Because if they cannot be measured simultaneously, you see that at every step you have some random probability to get other value of our observable. But if the values can be measured simultaneously, let's draw the same scheme. So we measure f. We decompose our function into the series an phi n. We get fn phi n with probability Pn equals to an squared. Okay, then we measure G. If we measure G, if these values can be measured simultaneously, then we do not need to decompose. Then we get Gn and the same state phi n. If because okay, let's say fn phi n. If the values f and g can be measured simultaneously, then after the second measurement, after the measurement of g, its measurement of f, we should get the same state, because after the third measurement, second measurement of f, we have with probability equals to 1 get a value f phi 1, because if we want to decompose fn by the functions by the eigenstates phi n, we understand that let's it be phi 2. We see that a2 should be equal to 1, n should be equal to 0 if n do not equal to 2. Only a2 survives and is equal to 1. So if we want to have to measure f1 with probability 1, as we do for values that can be measured simultaneously, the state shouldn't be changed after measurement of g. So if two values f and g can be measured simultaneously, then they have a common set of eigenfunctions. So the set of eigenfunctions phi n, it is common both for f and g, meaning that f acting fn will give us fn f phi n, and g acting on phi n give us gn phi n. So if two values can be measured simultaneously, after first act, we have some unknown probability and we get this state phi n. But after the second measurement, this state phi n is the eigenstate of G. And if it is an eigenstate of G, then with probability p equals to 1, we get the value Gn, not some other value, but Gn, which corresponds to the eigenstate phi n. And then if we see we didn't change our state after the measurement of G. So as we didn't change our state, our measurement after measurement of observable G, that means that measuring f one more time would give us the same Fn, because the state is the same, the eigenstate is the same, the eigenvalue should be same too. So probably the explanation was a bit messed up. Please ask the question if you didn't understand, but it is the crucial point in the measurement. When if two observables are not measurable simultaneously, cannot be measured together, it should be we should say together, not simultaneously, because there is no matter of equal moment of times. But if two variables cannot be measured together, then they do not have a common set of the eigenstates, and measurement of one value changes the state, changes the eigenstate that was before, and sequential measurement of observables G and F will give us hopping from phi 1 to some let's say phi 1, then H3, then with some non-zero probability we will get phi 4, 1, then with some non-zero probability we'll get, if we measure G, F, F, G, then with some non-zero probability we will get H10, then we will get phi 5, and etc. They do not measurement of value f erases information about the value g, and measurement of value g erases information about the value f, as it was in the example about the measurement of trajectory and velocity. But if these values can be measured together, then measurement of f gives us phi n, measurement of g gives us the same phi n, phi 2, let's say phi 2. Then the measurement of f have to bring us to phi 2, measurement g, the same phi 2, and to the infinity. So that is how things is done in quantum mechanics. I will return to this. I will return to this scheme in the next lecture, to remind you to how to understand the scheme one more time. But for now, I want to focus on that that equality. If we say that eigenstate or eigenfunction of value operator f of n is also the eigenfunction of g f gn. So yeah. Then let's look on the product of two operators f g acting on phi n. We will get f acting on g acting on phi n will give us gn phi n. Gn phi n. Gn is a number, so we can put it here, equals to gn f acting on phi n. But f acting on phi n, we know it's f fn phi n. We get gn fn phi n. So we see that phi n is also eigenstate of the product of these operators. Okay, let's calculate what we would get if we write down the operators in the reverse direction, phi n. Then acting fn on phi n will get us g fn phi n. That give us fn g acting on phi n plus fn times gn fn. But we know that fn times gn, if it is a number, then gn equals to fn. That means that if two observables can be measured simultaneously, then fg should be equal to gf. Or fg minus gf equals to 0. Let's move here. Yeah, that's our condition, and this this expression is called commutator f g. So if two values, that's the definition of commutator. If two values can be measured simultaneously, then their commutator g equals to 0. And if they cannot be measured simultaneously, their commutator is not 0. It's some value. So let's do this. Let's solve the one important problem to understand what commutator means, because if we are working, we all we're all used to work with real numbers, and in real numbers the order of terms in the products is not important, because a times b equals to b times a. But in operator algebra, it is important. The closest thing closest example is matrices, because in matrices you know that AB do not necessarily equals to BA. Actually, A and B matrices can have the shape that prevents even writing down this product. Let's say A is 1 0 2 2 3 0 5 4 0 1 0 2, and we can write down the multiplication of these matrices, but we cannot multiply in the reversed direction. We cannot multiply 5 4 or 1 or 2. No, we can. Yeah, but we will get multiplying this matrix, these two matrices. We will get matrix with size 2 by 2. You see, we should multiply this row by this column, this row by this column. No, it's not 2 by 2. It is, no, yeah, it's 2 by 2. And if we reverse these matrices, if we multiply matrix, which is, this matrix is 3 by 2 by matrix 2 by 3, we'll get the matrix 3 by 3. So you see that in matrices, the change in the order changes the size of the answer. Or even if we are working with the square matrices, let's multiply 0 0 0 0 1 1 0 by 1 minus 1 0. We get 0. Then we get minus 1 here, 1 here, and should be 0 here. Yeah. And let's reverse it. Multiply 1 0 0 minus 1 1. Yeah. We get row on the column give us 0. Here we get 1 row on the column. This row on this column we get minus 1, and this will give 0. So you see that these matrices are not equal. So the same is in the operator space. So let's calculate the commutator of these two operators. Operator x is just a multiplication on the variable x. Operator px, the projection of the momentum of the x-axis. Remember, it's minus h derivative a. So please calculate calculate this commutator, meaning you need to calculate the action of this commutator on some function f. So try to do that. We need to do px f minus pxx f. Take a couple of minutes. So let's solve this problem. Okay, px is just minus ih df over dx. Okay, minus minus IH derivative of the, we take the derivative. First of all, we act by x on f, we just multiply f, and then we have to act by this operator, the derivative, on the product x times f. Okay, here I will just move minus IH x times df dx. And here a minus times minus is plus IH. Then we need to take the derivative of this product.
H bar F.
Sorry. Do you want to say something? Okay. So IH times, so derivative of this product is just f plus x times df over dx. So here we have minus IH x times df dx, and here it is with the opposite sign, so we cancel it, and we get IH times f. That means that this operator acting, because the operator actually, commutator, is gives us an operator. This operator, this commutator acting on the f, gives us f multiplied by IH, which means that commutator x px equals to IH. That's it. That's how we find out what is commutator, what commutator is. So we can write down the basic properties of commutator. Here they are. I will prove them. This one is easy. AB minus BA. Commutator. This commutator is AB minus BA, and this commutator is minus BA minus AB. So you see that that's the same. So let's calculate this one. A commutates with B plus C. Okay, A B plus C minus B plus C A. Please be very careful with the order of the operator, because as you know, operator cannot be reordered in arbitrary way. So let's this multiplication gives us AB plus AC minus BA plus minus CA. We can write down it in the following way. AB minus BA plus AC minus CA equals to AB plus AC, because this is AB, commutator AB, and this one is commutator AC. So we proved the second line. Commutator A with the sum gives us the following. I will improve this one. Probably I will give you as a homework. Now what I want to do is to calculate two more commutators. The first one, what I want to say here, that we see that operator x, the coordinate operator, and the momentum operator px, the projection of the momentum on the x-axis, the commutator is not equal to 0. That means that these values, coordinate x, and projection of the momentum on the x-axis, cannot be measured simultaneously, cannot be measured together, because their commutator do not equal to 0. Let's calculate the commutator y px. So commutator of y coordinate with projection of the momentum on the another axis x. So here we have different axes, y and x. Okay, we can easily do that. It's y px f. Let's find out what is the action of this commutator on some function f. It's y py on f minus py, sorry, not py, but px y f. Okay, it's y times minus ih derivative of f with respect to x, minus ih derivative x y times f. Okay, here we have the same thing, minus ih y times df over dx, plus ih. Here we have to take the derivative of this product, y times f, but y do not depend on x, so we can move it here. We have y df over dx. We see that these two terms cancel each other, get 0. That means that we can measure the coordinate of the particle and the momentum simultaneously only if we're measuring the projection of the momentum on the on another axis. Then we measure the coordinate. So we can measure simultaneously y and px. We can simultaneously measure x and py, or z and px. They can be measured simultaneously. What cannot be measured simultaneously is x and projection of the cannot be measured simultaneously, or sorry, not y but x, y and py. Projection of the momentum, the coordinate of the particle along some axis cannot be measured simultaneously with projection of the momentum on the same axis. But if you're trying to measure coordinate and momentum corresponding to different axes, you can do that easily. So that's the first thing. The another thing, let's calculate. Let's calculate. Yeah, two more problems. First one is we'll do that later. Operator, let's calculate commutator x and p x y. Yeah, can do that. So we can use this equation. Obviously we can calculate it directly. We can act by this operator on some function f, um, then explicitly write down px, but it is a hard way, it is a long way. We can do it easily. We can use this this equation and write down that this commutator equals to commutator x px y plus px x y. Okay, xpx, we already know that xpx is equals to ih. xy, x and y both are just both operators just multiply some function on the real number, so the commutator equals to 0. That means that we have ihy plus 0 plus ihy. And the last thing I want to do is that no, I think that's all. So I'll give you. Oh no, I'm sorry. Let's combine our knowledge and check whether this operator is Hermitian. How can we do that? We should check whether x px conjugated equals to px. I'm sorry, equals to x px equals to it, itself. Okay, let's conjugate this operator, this product. We remember that conjugation of the product is the product of conjugated operators reversed. So px conjugated times x conjugated. But we know that a momentum operator and coordinate operator are Hermitian operator. So they equal to itself. The conjugated equals to itself. So we can write px x. However, so the left hand side gives us pxx, and the right hand side gives us xpx. But you already know that this equality do not hold, because px, the commutator pxx, do not equal to 0. That means that is why this product is not a Hermitian operator. And the last thing, let's look on this operator. We can do the same thing. Let's okay. Let's check whether this operator is Hermitian. We need to do it in that way. Py xpy minus y px minus y px. We know that let's look only on one term, xpy. xpy xpy conjugated xpy. Okay, let's conjugate it. The left hand side, xpy conjugated, Hermitian conjugated, equals to py conjugated times x conjugated. these are Hermitian operator, that is why this is py times x. So we should answer py x, is it the same as x py? But we have seen that these operators x and py, they commute. That means that we can switch the order in their product, and that means that this equation holds, and this term is Hermitian. The same we can say about this term, and that means the whole sum is a Hermitian operator. So that's how we use the commutators and how we can combine commutators, how we can use commutators to check the whether the operator is Hermitian and not. So what we have spoken today about is the procedure of the measurement. That's the major thing I want you to understand and remember, how the procedure of the measurement works in quantum mechanics, and how the measurement of one variable can change the state of the system and can erase the information about the another variable. And we saw that the commutators of the operator is how they linked with the simultaneous measurement, and we saw that if two operators commute with each other, so their commutator equals to 0, then they can be measured simultaneously. And if their commutator is not 0, they cannot be measured simultaneously. So that is all for today. Ask your questions if you have. Thank you.